Hello students, it's 9 o'clock sharp. Good morning. Hello, good morning.
Good morning, ma'am.
Very good. Lakshmi Prasanna, good morning. Okay, see, I'm taking attendance at the beginning of the class, in between, and also at the end of the class. But at the beginning, only 12 attendees are there. At the end, 60 or 64, 2 people are available, right? I really appreciate Section C students. You are attending very well. Out of 64 students, yesterday 62 have attended my class. I'm extremely happy about your participation, but maintain punctuality, right? Sharp at beginning of the class, that is at 9 o'clock, you must be available for the class, right? All those people indirectly, those who have attended, you will have some reward. Right, 9 o'clock, who all are available, everything is, I'm copying. Therefore, your attendance I'm copying at the beginning sharp at 9. So you will be rewarded, and you please encourage all others also to attend sharply at 9 o'clock. Now coming to our regular class, yesterday we have seen about single input balanced output differential amplifier. So it is a single input and only one input is there, therefore it is a single input. Other input is grounded, right? We have not connected here. Single input and output is taken at 2 collectors, therefore balanced output. Single input balanced output differential amplifier we have studied in the previous class. And for any amplifier we are calculating, in general we calculate voltage gain, current gain, input resistance and output resistance. Okay, and the current gain for differential amplifier is undefined, right? And therefore only 3 parameters we are calculating. What are the 3 parameters? One is the differential gain, voltage gain, that is differential voltage gain. In general we say differential gain, input resistance and output resistance. So to calculate this differential gain AD is equal to V naught by VI, otherwise V naught by V in, otherwise V naught by V in 1. Anything you can write, but follow the same notation. So V naught by V in. That means V in is a known voltage that we apply at the input terminals of the differential amplifier. And what is V naught? For this applied V in we are calculating. So to calculate that V naught, we are carrying out all AC analysis, DC analysis, all that. And finally, we are getting expression for V naught. After getting expression for V naught, we are calculating differential gain AD is equal to V naught by VI or V in, and finally we are getting the expression for AD. After that, what is RI? Input differential resistance, differential input resistance, and according to the definition we are defining. And after that, output resistance R naught. So all this we are doing. So for this, for త్రివేణి, నిమ్మగడ్డ త్రివేణి, నిమ్మగడ్డ త్రివేణి, త్రివేణి 425, 19 NG, lateral entry na? 425, Triveni. See, if one person disturbs the class, Triveni, you call me later. I don't want to waste my time. Right? Hello? Triveni?
అన్ఫార్చునేట్ గా జరిగిపోయింది అలా.
Okay. Then
Hello.
okay. No problem. Right. So if it is unexpected, okay. Right. Please maintain your devices carefully. Right. Okay. This is the circuit, and after that we have drawn a DC equivalent circuit. We know we have done thoroughly about dual input balanced output differential amplifier. So this is the DC equivalent circuit. I am telling you from the beginning. I think so far I have taken some 8 or 9 classes. So each and every class I have mentioned, right? Of course, first 2 classes we have not started differential amplifier. Of course, from the day I have started differential amplifiers, I am telling you how we draw DC equivalent circuit, right? So while drawing DC equivalent circuit, what we do? We short circuit AC input voltages. So V1 or V1 is not available here. You can see this. So V1 is short circuited, right? And after that, if we carry out analysis, that is Kirchhoff's voltage law at the input loop, and if we rearrange that equation like in dual input balanced output differential amplifier, we get expressions for IE and IVCEQ or ICQ and VCEQ, right? And after that we have carried out AC analysis, and in this AC analysis what we do? While carrying out AC analysis, we short circuit DC voltages. That means set DC voltages to 0. And then one more step is small signal T equivalent model. We replace transistor with its small signal T equivalent model. So by doing those 2 steps for the circuit shown here, for this circuit, if you do all that, and this is the equivalent circuit. Okay, this is the equivalent circuit. And when you draw this equivalent circuit, what I have done is I have modified this circuit. That means this RE is like this, and this small RE this side I have drawn, and this small RE this side I have drawn. So we brought this small that node to this, and after that this V in 1 and R in RS1 we have replaced with input resistance of the transistor, and then this terminal also we have connected to the ground. So similarly the other side also we have just extended this terminal to ground, and with reference to this line we have drawn this circuit diagram, right? So all the polarities, everything how we have indicated here, same thing is indicated in that circuit. So yesterday I have defined very clearly. So I hope all of you have followed and you have given good response. So like that, RA, this is RA, and RE right side one small RE, left side another small RE, and from that node V in one R in, and after that from collector that terminal resistor other end we have brought it to this ground, and similarly from other collector we brought resistance other end to this ground. Just for convenience sake we have redrawn this circuit. Okay, so why, what is the convenience that is required here? We want to draw we want to express IE1 and IE2 finally, right? Because we want to calculate what is the output that is available, because we are taking at collector 1 from here and also collector 2. So between these two, what is the total output voltage that we get? We are planning to calculate. We are trying to express that V naught. Therefore, for convenience sake, we have redrawn this equation in the same equation which is available here. This is redrawn in the procedure what I have mentioned earlier, right? Just what I have shown in the diagram. After drawing this circuit here, we have identified 2 loops. Any loop you can take. Okay, so what we have done is to make our life very simple. We have taken 2 overlapping loops only. So Kirchhoff's voltage law says that the algebraic sum of voltages in a closed loop equal to 0. So this is one component, this is another component, and this is another component, this is another component, and in this closed loop this is loop 1, right? So why I have shown you here means just for reference sake I have shown here. So why this red line means for understanding sake, while explanation only I can draw like this. Otherwise if I give you what is that loop 1, how I have shown in red color line, it will be clumsy. That's why I have not given that. So I have shown this loop 1 very clearly, right? So this is voltage source and voltage drop across R in 1, R in or R in 1, and voltage drop across RE, small re, voltage drop across capital RE. So this here only one point what we have to understand is this IE1 is entering into this node. After reaching this node, it is divided into two parts, right? So IE1, it is going in the other direction. This we have named it as IE2, and IE1 minus IE2 we have named it as I capital E, right? Current that is flowing through this capital RE. So we have indicated just otherwise you can give any other name also, right, for convenience sake. So to show that it is emitter current, I have given this name, that's all. So, and that is loop 1. Then after that we have taken loop 2, right? What is the purpose here? When we have two equations and two unknowns, it will be easy for us to apply our Cramer's rule, and will be easy for us to calculate what is IE1 and IE2, two unknowns. That's why by following that, these are the two equations we have written. Input voltage, then R in voltage drop across R in or R in 1, whatever you want you write. And after that, that RE and IE1 and loop 1, this is capital RE is there. So RE and I capital E is equal to 0. So that is loop 1, Kirchhoff's voltage law for loop 1. After that, KVL for loop 2. Up to this point, all the terms are same. Up to this point, all the terms are same, right? In loop 2, just I'll show again. In loop 2, instead of loop 1 we have considered here, right? Loop 1 in this way we have considered. Loop 2 we have considered in this manner, right? So therefore, this RE into IE2 term we get. So that is what I have shown here. RE into IE2. RE into IE2 is equal to 0, right? So these two equations I have mentioned very clearly yesterday. Once again, for the sake of slow learners, I am repeating and restating, right? After that, as usual, remaining analysis is same. IB1 you express in terms of IE1 by beta AC, IB2 IE2 by beta AC, then IE is equal to IE1 minus IE2. After that, you just take these terms and you neglect them. We know the reasons why we neglect, and then finally you can express equation 1 and 2 in this manner, right? After that, what we have done, two equations, two unknowns, IE1, IE2, V in 1, and IE1, IE2, V in 1, right? So then this we have arranged in matrix form. So using Cramer's rule, we can solve for IE1, IE2. So once if we have this matrix, blindly you can express what is delta 1, what is delta 2. Yesterday we have spent a lot of time. Just this is recap. So I'm going little faster. Delta 1 and delta 2, right? And after that, IE1 is equal to delta 1 by delta. IE2 is equal to delta 2 by delta. And IE1 we got it as V in 1 by 2RE, and IE2 we got as V in 1 by 2RE. That means IE1 and IE2 are same from this expression. So now what we have done finally, our aim is to express what is V0. For that, we try to carry out AC analysis and we try to find out what are the currents. So finally, V0, it is a balanced output differential amplifier. Single input and balanced output differential amplifier. Therefore, V0 is equal to VC2 minus VC1. And in the circuit yesterday, I have shown you clearly, IC1 is moving away from this resistor. Therefore, minus IC1 into RC is the voltage drop across the resistor. Therefore, IC2 RC minus of minus IC1 RC is the total voltage drop V0. So RC into IC1 plus IC2, IC1 is equal to IE1, IC2 is equal to IE2. Therefore, V0 expression you write RC, this RC, right, this RC, and in place of IE1, V in 1 by 2RE, in place of IE2, V in 1 by 2RE. So 2 V in 1 by 2RE, and finally you will get 2 gets cancelled and you will get V0 is equal to V in 1 into RC by RE, right? And after this what we do? One of you tell me. After this what we do? Yesterday itself we have answered. After calculating V naught, what we do?
Differential voltage gain.
Very good, very good. Differential voltage gain AD. AD is equal to V naught by V in 1. So we have expressed what is V naught and V in 1. So when these two terms gets cancelled, we get RC by RE, right? RC by RE, right? And after that, according to the definition of input resistance, after differential voltage gain, what we calculate? Differential resistance. What is the definition for differential resistance? Differential resistance is the resistance that can be measured at either input terminals when other terminal is grounded. That means differential input resistance can be measured either at input 1 or at input 2. Because it is only single input differential amplifier, now according to the definition, what we can say? Differential input resistance for this single input balanced output differential amplifier is the resistance defined as the resistance measured at input terminals when other terminal is grounded. Therefore, here we do not come across R in 1 and R in 2. We will get only R in 1. So, according to the definition, you just write the expression and you substitute the values of what is that? IE1 you will get. So, that is R in 1 is equal to V in 1 by IB1, and IB1 is equal to IE1 by beta AC, and beta AC comes to the numerator, IE1 will be in the denominator. So that IE1 expression you have V in 1 by RC by RE. So you substitute that, you will get it is equal to 2 times beta AC into RE. Similarly, what is the output resistance? R01 is equal to R02 is equal to RC. What is the definition for output resistance? Differential output resistance. This is the resistance measured at output terminal with respect to ground. With respect to ground. What is the output terminal? That collector VC1 is there we are at the collector of either transistor 1 or at the collector of the other transistor Q2. We measure the resistance with respect to ground, right? Therefore, R01 is equal to R02 is equal to RC. So like that yesterday we have defined what is that? We have derived the differential gain for single input unbalanced output, single input balanced output differential amplifier, and input resistance and also output resistance. After that we also have calculated single input unbalanced output differential amplifier, right? So why we call this as unbalanced output? Why we call this as unbalanced output?
We'll take
Output is taken at
only one collector.
Exactly. Very good, very good. I'm happy that you people are listening and following, right? Good students, section C, full attendance, and also you are following. That's good. You please keep it up. So V naught is taken at one collector only, right? So at the base of Q1 we have applied input, and at the collector of Q2 we have taken the output, right? So this is called single input unbalanced output differential amplifier. And what is the other name for this? Single input unbalanced differential amplifier. What is the other name? Other name for unbalanced output?
Single-ended.
Yes, exactly. Good. Right? Single-ended, or if it is a balanced output?
Double-ended.
Double-ended. Very good. Okay, so this is single input unbalanced output differential amplifier, right? So for that also the previous circuit, what all we have carried out the analysis, everything is same except only output is, earlier case we have taken output at two ends. Now in this case we take output at one end only. Therefore only that difference I am showing, and remaining all the steps that are to be repeated you repeat in your notebook. And probably today you have tomorrow you have third hour, no? tomorrow's third hour I will give you assignment questions, right? So those you can, you have to write and you have to upload your answers to the mail ID I give, right? So therefore, you keep ready all these, only derivation of all these 4 differential amplifiers I ask you to write separately again, right? So V naught is equal to Vc2 only. Previous case Vc2 minus Vc1. Now it is Vc2 only. Vc2 is nothing but Ic2RC. Ic2 is IE2. So IE2 expression is, what is IE2 expression? V in 1 by 2 Re. Therefore, V naught is equal to V in 1 by 2 Re into Rc, and differential gain definition we have written here, corresponding terms we have substituted. Because it is unbalanced output differential amplifier, it will be half of the balanced differential amplifier, balanced output differential amplifier. So we get AD is equal to RC by 2 RE, right? And after that, similar to the previous case, no change in the input and output. Therefore, what you have derived for single input balanced output differential amplifier, same thing you can consider. Only one difference is, for balanced output we take output at 2 terminals. For unbalanced output we take output at 1 terminal only. Therefore, instead of writing R01 is equal to R02 is equal to RC, we write R0 is equal to RC, because only at one end we are taking output. Okay. So all this we have discussed in yesterday's class, right? So all this is recap. Almost how much time I have taken to explain the concepts. 50% of that time or 80% of that time I have taken for recapping, because many of my students, they say that when you teach for the first time we hear, but when you restate again, though it takes more time, when you restate, then that will be very much useful for us. They said that's why, though it is taking more time, once again I am repeating and recapping, right? Now let us see the summary, right? So this summary is just for your reference sake. Okay, that means, okay, this is the summary, right? Summary of what all we have learned, right? There are 4 configurations. How many configurations are there in differential amplifiers?
4 configurations.
In
4
4 configurations. So out of 4, which one is more important?
Dual input balanced output.
Balanced output.
Dual input
All
balanced
other
output.
conditions, yes, all other conditions are covered in all other conditions are covered in this first one. Therefore, dual input balanced output is more important, right? So we have carried out AC and DC analysis. Because it is a balanced output differential amplifier, what is the differential gain? Differential gain is equal to
RC by RE.
RC by
RE.
RC by RE. Your voice is very low. Right. This voice is good. RC by RE. So where is the other balanced output amplifier? Third one. So for any balanced differential amplifier, gain is same, that is RC by RE. So if the amplifier is unbalanced, then what will happen? Gain will be
Half of the gain.
Double.
yes, double or half. Lot of difference is there. If you have
Half
1 lakh rupees,
Half.
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 Someone said double, right? Be careful. If you have 1 lakh rupees, 1 lakh rupees, right? If you put it in the bank, if it becomes double, it will become 2 lakhs, right? Otherwise, if it is reduced to half, how much it will be?
50,000.
50,000. So there is a lot of difference between 50,000 and 2 lakhs, right? So double or half. This is the what I say in IES or some GATE or some such exams. This type of questions will be there, whether it is half or doubled or quadrupled or none of these. Some people, something madam mentioned, whether it is doubled or half. Okay, let us write double. Some people think, okay, let me write half. So then accuracy is more important. Those who write half only will get 1 mark, and those who have written double, they lose 0.5 or 0.25 marks, right? So like that. So accuracy is also very important. So how do you remember whether it is doubled or half or same? Because for balanced output amplifier, you are taking output at double-ended, two ends, right? So therefore, you are getting RC by RE. And for unbalanced differential amplifier, you are taking output at one end only, right? Therefore, it is halved. It is halved, right? So like that, you can remember it is unbalanced differential amplifier means it is half of the balanced differential amplifier. So that's why for unbalanced differential amplifier and for this unbalanced differential amplifier also RC by 2RE is the differential gain. So all these expressions we have derived in an identical manner. We have taken the corresponding configuration circuit. We have carried out, we understood that DC analysis is same for all 4 configurations, and then we have carried out AC analysis and we have obtained these expressions, right? And after that, we know how the differential input resistance is defined, right? So for all 4 differential amplifiers, the definition is same. Only thing is, if it is dual input and balanced output differential amplifier, R in 1 is equal to R in 2 is equal to this much, and R01 is equal to R02 is equal to this much you will get. If it is dual input, you will get R in 1, R in 2. If it is a single-ended output, you will get R0 only. So only from the name, there are some minor modifications, that's all. Otherwise, you say differential resistance is same, right? Differential input resistance and output resistance, both are same for all 4 configurations, right? So now you tell me whether this differential amplifiers topic is very easy or very tough.
Very easy, ma'am.
Very easy. What you have to remember is just Kramer's rule, which is familiar to us. Only thing before the exam, once if you remember that equivalent circuit how we draw, that is sufficient. Okay. So very easily from unit 1 in your question paper, out of these 4 questions, each one of you in each set we will get 1 question from these 4. So these 4 will be available in your question paper. So that too here it is like buy one get two, right? It is like buy one. It is like buy one and get two offers we see in many shopping malls. Now here I can say learn one and get 4 answers, right? Learn one and get 4 answers. So it is a very simplest unit. Only thing is by seeing the what is that circuits, you people, some of you will get phobia. Otherwise, if you just take one step into the sea, it will be very easy, right? So with this conclusion, I am planning to move forward, right? So teaching this in a very clear manner, my job is over, right? Now I want to test your knowledge also. So what I believe is, if you know how to write all the steps by seeing the notes, even without seeing the notes also you will be able to write. That's why what I ask you to do is, I ask you to write assignment and submit. So I'll give you those questions, okay? So meanwhile you can start writing these answers, but tomorrow only I want to give you this. Dictating these questions is not good in online. Therefore I want to give you these questions. Preferably I'll see whether I want to give Google form or I want to give you slide. All that I try to see, right? So even if it is Google form also, you can write and upload your answer. That option also I will give. But only thing is my Google account drive will be occupied by your assignments. So for that, what is the other solution I am trying to see. Okay. So but you people be ready in your notebooks. Put heading dual input balanced output differential amplifier and carry out analysis and obtain these 3 expressions. After that, you take dual input unbalanced output differential amplifier in your notebook, write and keep it ready. Again, single input balanced output, single input unbalanced output, 4 clearly derivations you do, and keep it ready in your notebooks, right? So with these few concepts, now I am going to move forward. Now I can say at the beginning of this class you do not know what is a differential amplifier. Now you have become experts in understanding what is a differential amplifier, right? So with this basic concept, now we are going into the next step, that is the swamping resistors. Okay, before that I have mentioned the current gain of the differential amplifier is undefined, and it is generally used as a voltage amplifier. Differential amplifier is generally used as a voltage amplifier, not as current amplifier. Okay, so next discussions you will understand why it is not used as current amplifier. Okay, so current gain is undefined. Okay, now let us see the swamping resistors. Okay, here itself let me also tell you, because the input resistance we make very high, right? For this differential amplifier we make this input resistance very high, right? When input resistance is equal to very high means, okay, let us say 1 kilo ohm. Is there any chance to have input current? Okay, this is the voltage and this is the resistance. Okay, now if the input resistance is 1 kilo ohm and there is some voltage here, there is a chance for having some input current. Okay, now if this input resistance is increased to 1 mega ohms, right? Then what happens to the current, ma? Increases or decreases? Resistance is increased, Emma?
Decreases.
Decreases. Very good.
Decreases.
Now, right, instead of 1 mega ohm I make it very very high value, almost like infinity. If the resistance is very high, what happens? It will be like open circuit. Okay, if the resistance is 0, it is equivalent to, if the resistance is 0, it is equivalent to
Open circuit.
Closed circuit.
Short circuit.
short circuit. Very good. Closed circuit or short circuit, right? That's why maximum current flows, right? Now if the resistance is made very large, we can say it is almost like open circuit. Therefore what about current?
Does not flow.
Yes.
Zero.
Okay. Almost 0, right? It will be 0. That means at the input, if we make very very high resistance, then there is a chance of having very low current. So therefore there is no chance of having current amplification, right? So what we do is we try to make this differential amplifier as voltage amplifier only, and therefore we try to keep its input resistance very very high. That's why we use very high input devices, right? So you tell me one device which is having very high input resistance. Yes?
Water heater.
No, electronic component, electronic device, active component. Yes? Have you heard about field effect transistor? FET.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
One of the basic properties of field effect transistor is its input resistance is very high, right? So like that, here what happens means this differential amplifier current gain is undefined. Okay, so you will come across this once again. So now let us see some swamping resistors concept here, right? So let me show you this circuit. This is, what is this circuit? Can you identify? What is this circuit?
Dual input balance.
Balanced output differential.
Very good, very good. Okay. Dual input and a balanced output. Differential.
Unbalanced output.
Balanced or
Amplifier.
unbalanced?
Balanced.
Balanced, ma'am.
Yes,
Balanced.
Balanced.
balanced output, differential.
Balanced.
Okay, good. Right. Now for dual input balanced output differential amplifier, what is the current voltage gain that we have defined? Voltage gain that we have defined, AD is equal to
RC by
RC
RE.
by RE.
RC by RE. What is this small RE?
RE.
This is the emitter resistance. Okay, right. So what is this value of this RE? It is very, very small or high? Small RE.
Small, ma'am.
It is very, very small. How we are saying compared to RE, capital RE is far, far greater than small RE. Capital RE is far, far greater than small RE. So this is in the order of tens of ohms only. That means 22 ohms or 33 ohms, like that, very few ohms. Whereas R capital E, that this is biasing resistance. This is in the order of kilo ohms, maybe 3.3 kilo ohms or 8.2 kilo ohms. We have done some problems. Okay. So now, if this denominator is small, for example, let us take this as some, what is that I have written, because right, I have written these values. Okay. Right. If RE, I think in my rough notes only I have written. Okay. Anyhow, I can tell you, just for clarification sake, I have written, I think. So you take RE value some 22 ohms like that. Denominator is very small, right? Denominator is very small. Now numerator, let us take 3.3 kilo ohms or something. Okay. Now 3.3 kilo ohms divided by this small RE, right? Okay. RE, capital RE, all of you take one example. Capital RE is equal to 10 kilo ohms. All of you write, capital RE is equal to 10 kilo ohms. Right. Small RE is equal to 22 ohms. Small RE is equal to 22 ohms. And RC is equal to 3.3 kilo ohms. RC is equal to 3.3 kilo ohms. Right. RE 10 kilo ohms, small RE 22 ohms, RC 3.3 kilo ohms, right? Now when RE is small, that means RE is equal to 22 ohms and RC equal to 3.3 K, what is the differential gain AD? Calculate and tell me what is the differential gain AD?
150.
Yes, 150, right? 150, very good. You people are very fast. I'm happy. All others also please calculate, just a simple calculation. So now after giving the problem, if you run for calculator or if you do not know how to calculate from your mobile, it will take more time. Otherwise, who is that who answered as 150? Tell me your name.
C4. C4.
Pardon? What is that?
C4, madam.
I asked name, no? Name means name you have to give.
Sai Krishna, madam.
Sai Krishna, very good, Sai Krishna. Right, Sai Krishna. Good response. Right. Even whether it is good or bad, all you, everything I am writing, because if I remember only your only bad things, it is not, no way it is going to help us. Therefore, I remember all good people and also the other people unknowingly or knowingly who disturb my class, right? So therefore, Sai Krishna, it's good. And today Akhil also is answering. Akhil also is answering, I think. Good. Okay. Then 150 it is. Okay. That means now you this 22, if it is made into some 10 or 33, there will be some huge variation. Now in the denominator, that means in place of small RE, what you do is you add denominator, you write in place of RE, you write RE plus capital RE. RE plus capital RE. Let us name this as RE dash. Capital RE value I have given you already. So in place of RE, if we add RE, capital RE also. Now you calculate differential gain. Differential gain is equal to RC by small re plus capital RE. That means 3.3K divided by 10K plus 22 ohms. How much it will be? Te- 3.3K divided by 10K plus 22. How much it will be?
32.9.
32.9. Once again verify 3.3K.
93 point something, ma'am.
93. No. 3.3K.
0.33.
Yes, yes, exactly. It is 0.33 or 0.329 I got. Okay, 329 means 33.
3 point
So
కదా?
0.33.
Okay.
Yes. Okay. So it is 0.3. That means if the denominator is higher in value, right? Differential gain, variation in differential gain will be smaller. That means now here what we want to convey is, if we take right instead of small re, if there are any variations in small re, the gain of the differential amplifier varies accordingly, right? That means it will vary rapidly because re is smaller value. So if there are any small variations in re, the differential gain of the amplifier varies rapidly, right? Because its magnitude is 150, like that. But if we add some more resistance here, that means some biasing resistance itself, or some resistors which we name them as swamping resistors here. That means because small re is disturbing the gain of the amplifier. Small re is 22. It's I mean, what is this small re we have calculated in a problem? It is 26 millivolts by IE. So if there are any, what is this 26 millivolts? Temperature, it depends on temperature, volt equivalent of temperature. So due to variations in temperature, if there are variations in volt equivalent of temperature, then there will be variations in RE. So those variations will affect the gain of the differential amplifier. So we don't want that, because at various temperature ranges, temperature variations, whenever there is variation in temperature, there should not be any variation in the differential gain. So to keep it more linear and constant, what we do is we try to reduce this effect of small re. Therefore what we do is we add some more resistance. We name those resistors as swamping resistors. So these swamping resistors, they fill the effect of this RE. That's why these resistors are called swamping resistors, right? What is this RE and RC? These are called, this is a load resistor. RE is called a biasing resistor. So you have what is that? Different biasing techniques, all that. So like that, this RE dash is called as swamping resistor, right? So that is what I want to convey from this circuit. So let me tell you the importance of the same thing. As we use this method, AD increases, right? And there will be some limitations. Therefore, there are some limitations with this. When we add this one more resistor in the circuit, what will happen? One more resistor we have added in the circuit. Okay, so that means one more component you have added, right? You are taking flight journey, so your maximum travel bag weight should be 25 kgs only, right? But suddenly you want to add one more packet in your bag, then what will happen? Weight of the bag will be increasing, right? And not only weight, area also increases. So that is the disadvantage. So for that, what you have to do, you are ready to pay that extra charge also. So like that here also, because we have added one more resistor here and one more resistor here, when this is fabricated in the chip form, in an IC form, IC area increases, because if the number of components increases, naturally more material is required and IC chip area also increases, right? So that is the disadvantage with this swamping resistors. And also this shows the effect on temperature. That means when there are variations in temperature, what is that? These resistors, they are showing their effect on temperature, and there will be a shift in Q point, because this is the emitter resistance RE, right? This is the biasing resistance. Now you have added one more RE here. Therefore, all Q point, everything will be changing. So like that, these are some effects of these swamping resistors, but still we are ready to bear that. Okay, these are the three limitations, right? So therefore, what we do is different devices, right? We use, that is, one is Darlington pair. What is this Darlington pair? What are the pair of resistors here? What are the pair of amplifiers here? Which type of amplifiers are paired? Yes? Darlington pair. Have you heard about Darlington pair? Yes or no?
Yes, ma'am.
Yes. Okay.
Yes, ma'am.
You recollect and tell me tomorrow also when I recap. I will ask again what is a Darlington pair. Then have you studied field effect transistor?
Yes, ma'am.
Yes, field effect
Yes, ma'am.
transistor. Just now I have mentioned in the previous explanation that it is a very high input resistance. It is having very high input resistance. The other one is swamping resistors, right? So, right. These are the three methods that can be used. Now in this class we are going to learn about swamping resistors. So what are the swamping resistors? These are the resistors connected in series with emitter resistance, right? So okay, these are the resistors connected in series with emitter resistance, not to reduce, to increase resistance, sorry, right? So to increase resistance, you please write. To increase the input resistance. By mistake we have written here to reduce, it is to increase the input resistance, right? So the circuit is shown below. This is the circuit with swamping resistor, right? This is the circuit with swamping resistors. Have you followed? What is a swamping resistor? To reduce the effect of small RE, where the differential gain of the differential amplifier depends on small RE. When there are small variations in RE, gain of the amplifier is varying rapidly. Therefore, to reduce the effect of RE on AD, we can use different methods. One is swamping resistors, other one is Darlington pair amplifier, other one is field effect transistor. Now here we are talking about swamping resistors. So this swamping resistor means one more resistor, that is same RE, can be added here. So that means RE dash we are writing, that's why, right? We are writing this as RE dash. So these swamping resistors, dual input balanced output differential amplifier, and Q1, Q2, all these are known things only, just for information sake I have mentioned here, that's all. So now when you replace this RE by RE plus RE, right? Small RE, differential gain, just now I have written RC by differential gain is equal to this, you please note down, right? All the explanation I have given you, RC by small RE plus capital RE, right? Capital RE. That means this is the resistance that we are adding, swamping resistance. That means RE dash. RE dash.
భజంత్రీలు లేవు.
Naveen. 434 Naveen. What is that? Paper? Naveen. 434 Naveen. See, he heard my voice and he has muted, but not saying anything. Okay, 434 Naveen, also you call me later. Let me take your attendance also once. Anyhow, Naveen has disturbed our class. Those who disturb my class, they will pay. Right. Now, AD is equal to RC by RE actually. Now, what we are doing? We are adding some more resistance RE dash. What is this RE dash? Now, wherever we have RE, we are writing RE dash also. That means we are adding some RE dash, right? So that means this RE dash is nothing but swamping resistor. So now new voltage gain or new differential voltage gain is equal to RC by RE plus some swamping resistor RE dash. And similarly, when you add this swamping resistor, R in 1 is equal to R in 2 is equal to 2 beta AC occur. We are saying, right? 2 beta AC is outside. RE in place of RE, now what we are writing is RE plus RE dash. RE plus RE dash. And similarly, output resistance, it doesn't affect because it is independent of RE dash. Only input side we have some variation, right? So like this, we will be able to reduce the effect of swamping resistors, right? So have you followed what is the purpose of these swamping resistors? Have you followed what is the purpose of these swamping resistors? What is the
Yes, ma'am.
purpose of yes. What is the purpose of swamping resistor?
To reduce.
To reduce the impact of RE.
Res-
To reduce the impact of
Resistance
RE.
of RE.
Impact of RE on differential gain of the amplifier, right? So to reduce, because differential gain of all the 4 configurations of differential amplifiers is either RC by RE or it is RC by 2RE. So if there are any variations in small RE, there will be huge variations in differential gain. So we do not want that. Gain should be stable throughout. That means gain should be stable like that, but it should not be like this. As the temperature increases, gain increase, like that we do not like. So we like to maintain stable gain. Therefore, we are trying to reduce the effect of small RE on differential gain either by using 3 methods. What are the 3 methods? One is using Darlington pair. Second one is using, that means by adding this, what we do is we increase the input resistance. You just observe, input resistance of the differential amplifier is equal to 2 times beta into RC plus RE plus RA dash. So this swamping resistor directly increases the input resistance. So if the differential amplifier circuit is designed with BJT, simply by adding swamping resistors, you can increase the input resistance of the differential amplifier, and you will have what is that linear range of amplification. Otherwise, you can also, instead of using swamping resistor, what can you use to increase the input resistance? You can use, what can you use?
FET.
Yes, you can use
FET.
field effect transistor. Otherwise, you can also use
Darlington.
yes, Darlington pair amplifier. Anyone got into your mind what is a Darlington amplifier? What is a Darlington pair? Right? So if will you verify for tomorrow and come?
Connecting
ma'am.
of 2
Yes, ma'am.
transistors, ma'am, in compounding form.
Two
Okay,
transistors,
what
ma'am.
configuration?
In parallel.
What configuration it is?
CE, ma'am.
See, we verify once. What we have connected is CE only now, till now.
Transistors. Multiple transistors.
Okay, okay. Right. Once you just verify what is a Darlington amplifier, what are its properties, right? So here
Okay.
high input resistance is required. From that you understand that this Darlington pair has high input impedance, right? So for tomorrow, this is the assignment for you. That is assignment means just question for you. That is what is a Darlington pair amplifier. Okay, right. Now either FET or Darlington pair or swamping resistor. These are the three components that you can use. So in this class, what we have studied is swamping resistors. Swamping resistors. Now let us see some advantages of swamping resistors. Right. So we are coming to the end of the class. Let us again once again we have to go backward and we have to verify once again. So let me move a little faster. Advantages of swamping resistors, right? So what is the actually what is the problem? Its input resistance, right? Advantages of swamping resistors: input resistance is very high. How input resistance is high? We have just seen in the Ri is equal to Ri2 is equal to 2 beta Re plus Re dash. Re dash is the swamping resistor. Depending on this swamping resistor, if it is let us say Re is very small, Re dash is some 1 kilo ohm. If you make it 2 kilo ohms, 2 kilo ohms into beta into 2 means very high input resistance you will get, right? So the selection of swamping resistor, depending on the gain of the amplifier, all other requirements, we will be able to select the value of swamping resistor. But in general, they are very high resistances. Okay. Then what is the other advantage of this swamping resistor is increases the linearity range. That means this range will be increased, right? Otherwise what will happen if there is variation in temperature increase and decrease? So gain will be zigzag, right? So instead of that, when you use this, that means this is gain is zigzag when we have only small Re. If we have this swamping resistor also, then linearity range of the amplifier increases. So therefore this steady linear amplification is required for us. And therefore if your internet connection is going and coming, you are getting connection and disconnected, all that zigzag manner connected means you lose a lot of information. Similarly, if you have steady current steady connection, you will not miss anything. So of course for your differential amplifier, linearity range is more important. Therefore that is another advantage. Then uh, next advantage is minimization of changes in transistor parameters due to temperature, right? Because of the temperature variations, there will be variation in parameters. That effect will not be there on the gain of the amplifier. So with all these advantages, we prefer swamping resistors, right? So with swamping resistors, what is that? What are the advantages you have seen? Let me move little back once again and let me tell you. So after this summary in today's class, once again let me take your attendance also. There are 61 students, but because all 61 students are here, I am telling you again, sharp at 9 o'clock I am taking attendance. Sharp at 9, there are something around 18 or 19 students, and by the time I download it was 20, that's all. But at the end of the class, 61, right? You are connected and you are staying, but late comers, we will not give attendance. Okay, you may lose your attendance. Therefore, please maintain punctuality and try to join the class sharp at 9 o'clock, right? At the beginning of the class, you please join, right? Attendance, right? Okay. So for today's class, we have seen this summary, and after this summary, we have seen the current gain, why it is undefined, very high input, almost like open, so no input current. So that's why we use this amplifier as voltage amplifier only, and because of the variations in small RE, there is a chance for variations in AD, and we want to make these variations linear, right, stable. That's why we are adding some type of resistors, and we are planning to increase the input resistance of the differential amplifier. So this differential amplifier input resistance can be increased by three different ways. What are the three different ways means? First one is use of differential Darlington pair amplifier and use of field effect transistor using swamping resistors. And after that, we have used the swamping resistors, and then we have modified the expressions, that is AD, RI and R0. And after that, we have seen the advantages of swamping resistors, right? So with this, I want to stop my today's class, right? So all of you please study well and get ready for your assignment. Right? Get ready for your attendance. Sorry, get ready for your next class. And let me once again, right. So out of 60, one number left already, right? Okay, with this I'm stopping. You please, you can leave this class and make your assignments ready, right? Okay, wish you all the best.
Thank you, ma'am.
Thank
Okay,
you,
God
ma'am.
bless you all. God bless you all.
Thank you, ma'am.
Sai Krishna. Yes, yes.